There is a theory according to which aliens contributed to human technological evolution. In reality, things didn't exactly happen that way. It has taken several hundred years to only partially define the large number of microscopic atomic particles that make up everything around us, including us ourselves. These discoveries were only later used for the construction of new, high-performance and technologically advanced machinery and equipment. However, it could be that some aliens are trying to defend our planet, but from us ourselves. Given that, the visits of these entities from outer space would seem directly proportional to the first Trinity test, which took place on July 16, 1945 in New Mexico, and the subsequent 2058 nuclear tests that have been conducted around the world. Only through the intertwining of complex history is it possible to observe links between the end of World War II and the beginning of modern ufology, but above all between the world of science and political power. Over the course of about 300 years, our reality has undergone changes at a very high rate. Atoms, recognized by John Dalton as early as 1803 as the fundamental constituents of the molecules of all matter, 66 years later were catalogued in the periodic table of elements, according to their chemical properties, starting the study of the structure of the elements. Only at the end of the 19th century were radiation and matter defined both as wave phenomena and as particle entities. Physical characteristics in stark contrast to the view of classical mechanics that had prevailed until then. Quantum mechanics, together with a theory of relativity, thus became the watershed of classical physics that led to the birth of modern physics. But what exactly is quantum mechanics? It is a physical theory that describes the behavior of subatomic particles, such as electrons, photons, and systems in general, at the microscopic level. Its progressive study has caused very profound changes on the conception of reality. For example, quantum entanglement, formulated by a group of theoretical physicists, including Einstein, Podolsky and Rosen, and called the EPR paradox, describes a hypothetical situation in which two particles possess properties capable of remaining connected to each other, even at very large distances from each other. For example, if two photons are entangled, their quantum properties, such as polarization, spin, or position, remain interconnected. Even if these photons were separated and moved very large distances from each other, any change made on the state of one will instantly affect the other. Over time, this phenomenon has become a specific feature of quantum mechanics, and to date, this branch of physics has made it possible to build extraordinary objects in the most disparate fields, such as high-speed microprocessors and flash memories, thanks to tunneling transistors, optical instruments such as diffraction lenses and lasers used in the medical field for the diagnosis and treatment of diseases, or for the production of high-resolution medical images, and many, many more. It could also be said that since the Industrial Revolution, most of the technology built using classical physics and produced in the space of about 300 years has become semi-obsolete or totally superseded thanks to quantum mechanics. The scientists who contributed to studies in this area in the period between the two world wars, inserted in academic environments where few could access them, carried out their projects, overcoming the limits imposed by dictatorships, with many difficulties, since they were inevitably placed under the scrutiny of the political world. Thus, it was that some of them, in a sort of butterfly effect, wrote the destiny of humanity in history. Among these, the most important for his engineering contribution concerning the first atomic bomb is also Enrico Fermi, the scientist who collaborated with Oppenheimer and the first who theorized the famous paradox on the presence of aliens in the universe. The youngest of 3 children in a modest bourgeois family, from an early age he showed an exceptional memory and a surprising intelligence that allowed him to excel in his studies. Following his older brother's death during a simple surgery, he followed his calling by completing high school a year early. One of the first sources he drew upon was a treatise dated 1840, found in the Roman market of Campo de' Fiori and entitled Elementorum Physicae Mathematicae, which became the foundation of the young man's studies. The 900-page book in Latin on subjects of mathematics, classical mechanics, astronomy, optics and acoustics had been studied by many during the years and was filled with notes. His intelligence surprised the people around him throughout his life, and in particular during his high school years, where the engineer Adolfo Amidei, a colleague of his father, guided his training. Fermi, despite his age, read university textbooks until 1918, the year in which Amidei suggested that he enroll at the University of Pisa instead of studying in Rome. Here, the young man took part in the selection process to enter the prestigious Scuola Normale Superiore by facing a test on the distinctive characteristics of sounds and their causes. His solutions were presented in 7 pages in which the production and propagation of sound were discussed. The order in which the solutions were written amazed the professors. Fermi himself claimed that the technique he had used had helped. The rough copy of the assignment, 7 atypically chaotic pages, were written in the reverse order of the final copy. During his university life, his fame among the professors grew to such an extent that some of them often asked to have private conversations with him, and he studied in complete autonomy and freedom, since he was already aware of a large part of the university program. One of his professors of experimental physics, Luigi Puccianti, sometimes asked him to teach him something that he could still learn. Fermi himself wrote to his friend Persico, "At the Institute of Physics, I am gradually becoming the most influential authority. One of these days, I will have to give, in front of various tycoons, a lecture on quantum theory, of which I am always a propagandist." Aware of his abilities and close to completing his training course, he chose the field that offered the best research possibilities, took all the material collected up to then, and asked himself a simple question: why concentrate only on one of the research methods? At the time, in Italy, theoretical physics was not recognized as a university discipline, and a thesis in that area would have attracted the indignation of older professors. The closest thing to theoretical physics was mechanics, taught by mathematicians, who left out all the physical implications in favor of a rigorous mathematical approach. These circumstances also explain why quantum mechanics did not immediately take hold in Italy. It was considered a no-man's land between physics and mathematics. Fermi then began his experimental thesis on X-ray diffraction images produced by curved crystals. He made the X-ray tubes himself, together with 2 other students and friends, Nello Carrara and Franco Rasetti. The group often experimented in the laboratory of the University of Pisa, obtaining free access from the head of the institute. Thus he demonstrated that he was a complete physicist, carrying out an experimental thesis, even though he was already known as a theorist. With his degree and a magna cum laude in 1924, he presented himself to Professor Orso Mario Corbino, director of the institute in Via Panisperna in Rome, who showed him a possible path to follow. Fermi was to continue his work in Germany, in Göttingen, with Max Born, and later in Holland, in Leiden with Paul Ehrenfest, the same physicist who in 1928 reportedly responded to Oppenheimer's request for access by implying that there were a multitude of issues beyond just physics that they needed to talk about. A year after that meeting with Corbino, Fermi was initiated into the Adriano Lemmi Masonic Lodge of the Grand Orient of Italy, in Rome, something that has always aroused suspicions relating to Masonic implication, albeit indirectly, in the creation of the first atomic bomb. With the advent of fascism, the members of different Italian Masonic groups grew in number, and even the Quadrumvirs who accompanied Benito Mussolini on the March on Rome were all affiliated to different lodges. According to the American essayist Peter Tompkins, a former agent of the Office of Strategic Services, the American Secret Service forerunner of the CIA, Corbino, as a Freemason, would have obtained economic bribes through the Sinclair Oil Company. In his volume From the Duce's Secret Papers, the essayist observes that this maneuver would also have been one of the many reasons that led to the assassination of anti-fascist politician Giacomo Matteotti, which took place on the 10th of June 1924. Mussolini would have been in possession of the papers capable of attesting to the matter, and according to many enthusiasts of the subject, that of the despot was a diversion adopted in order to get hold of the bribes and finance specific projects without Corbino's knowledge. Corbino, despite coming from a not wealthy family, during his brilliant career as a physicist proved many times to be a charismatic mediator, and in addition to being called between 1910 and 1920 to take part in managerial commitments related to the development and search for funds for engineering works in the hydroelectric sector, and his studies on experimental military weapons in the Galician period, in 1918 he became the director and head of the institute in Via Panisperna. When Fermi presented himself to Corbino, the director of the institute was already in the good graces of Mussolini, who personally called him to the position of Minister of the National Economy in the 1923-1924 mandate. Although Corbino had never enrolled in the fascist party, Mussolini probably saw in him someone capable of attracting, thanks to his fame, different and possible supporters of the regime. The role of director of the institute thus became economically and logistically fundamental for the progress of his research. He organized important events attended by very famous European scientists, managed to find funds for research despite poverty and desperation spreading throughout the country, and played a pivotal role that is very often overlooked. Through his talent as a political outsider, he managed to juggle between his impositions with dexterity, giving different possibilities to young scientists who, one day, in turn, would have given birth to Italian research on the atom. When Corbino in 1924 advised Fermi to continue his studies in Leiden in the Netherlands with Paul Ehrenfest, he took a very important step forwards. Fermi had to be acquainted with the places where modern physics was already breaking new ground. Oppenheimer himself applied to enter the institute the year following Fermi's entry. To Oppenheimer's letter, Professor Ehrenfest replied, "If you wish to further increase your mathematical artillery in the next few years in Europe, I should ask you not only not to come to Leiden, but if possible, not even to Holland. And I only ask you this because I am fond of you, and I don't want to take you away from your path. But if, on the contrary, you want to spend at least your first few months patiently, comfortably, and pleasantly in discussions that always return to the same points, chatting about a few fundamental questions with me and with our young people, without thinking too much about publications, well, then I will welcome you with open arms." In 1926, Oppenheimer entered the institute. Years later, the Great Depression hit the world economy, causing social tension that paved the way for Hitler's Nazi Germany. During the time that Oppenheimer attended Leiden University, National Socialism was not yet in power in Germany. However, there were signs of an emerging nationalist and anti-democratic sentiment in Europe, but the full extent and rise of National Socialism as a political movement had not yet been clearly recognized. Although the terrible and well-known political situation of Nazi Germany was yet to develop, it is very probable that Ehrenfest and other scientists feared a possible overthrow of German democracy, and it is therefore also very probable that some of them anticipated their studies related to the atomic bomb, including Fermi himself. Hitler himself wrote, "Already in the years 1913-1914, I began to express in various circles, today loyal to the National Socialist cause, the thought that the question of the future of Germany revolved around the destruction of Marxism." While Albert Einstein wrote to his sister Maya in August 1922, "Dark times are brewing here, politically and economically, and I'm happy to get away from it all for a year and a half." Among the physicists able to understand the possible socio-political trends in a forward-looking way was probably also Ehrenfest, who had Austrian origins, just like Hitler. If already in 1919 anti-Semitic sentiments began to surface in neighbouring Austria, it is highly probable that the German people were already slowly aligning themselves with the thoughts that Nazism years later used to control society. The people felt strong resentment towards the Weimar Republic and the loss of the First World War. The war brought hunger, poverty, and Hitler clung to this general discontent, fomenting racial concepts. He blamed the Jews for stoking the Bolshevik revolutionary hotbeds, which allegedly undermined the resistance of the soldiers at the front from within, leading the politicians, also known as the November Criminals, to surrender and sign the Treaty of Versailles. The first symptom of change appeared on November 8, 1923, with the Munich Putsch. The Nazis moved from a beer hall to the Bavarian War Ministry, intending to overthrow the right-wing separatist government of Bavaria, and from there march on Berlin, emulating Mussolini's March on Rome. Hitler, on that occasion, enlisted the help of ex-combatants disillusioned by the Weimar Republic, who were members of the paramilitary organizations of the Franks Corps. The coup failed and Hitler was tried for high treason. However, he used the trial to spread his message throughout Germany. The year Fermi met Corbino, in April 1924, Hitler was sentenced to 5 years in prison, about 80 kilometers from Munich. Here he read Henry Ford's work, The International Jew, and inspired by this, he wrote his famous Mein Kampf. This ponderous work, containing ideas on race, history and politics, and including numerous warnings about the fate that awaited his enemies if he were to rise to power, was first published in 2 volumes, the first in 1925 and the second a year later. The possibilities of Hitler gaining power seemed so remote at the time that no one took his writings seriously. Considered relatively harmless, Hitler was granted a reduced sentence and was released in 1924 after only 9 months in prison. At that time, the Nazi Party barely existed, and during these years a group was formed which would later become one of the key tools in achieving the dictator's goals. In 1925, he formed a personal bodyguard unit, the Schutzstaffel, or Protection Unit, or SS, which was led by Heinrich Himmler, the main executor of the plans on the Jewish question during World War II. The turning point in the dictator's fortunes came with the Great Depression that reached Germany in 1930, the year in which Hitler assumed the position of Oberst SA, or Supreme Leader. But as early as 1926, German scientists were not living on a happy island where they could only occupy themselves with science and research, far from ideology and politics. Although some escaped the regime in Italy, in Germany the matter must have been very different. With World War II, German physicists had to demonstrate their contribution to victory, otherwise they risked being sent to the front as soldiers. Among them, there were also staunch supporters of the regime, above all supporters of a policy of racial hygiene intended to shape the nation, and which included, in particular, the prevention of certain hereditary diseases, but at the same time also contemplated considerations on the physical elimination of people born with congenital defects, already advanced concepts at the end of the 19th century. It is therefore not surprising that during the Nazi years some groups of graduates were particularly politicized. Among doctors, for example, almost half enrolled in the National Socialist Party, and a part of the doctors and psychiatrists were involved not only in state juridical sentences on the racially or hereditarily healthy state of their German patients, but also in the forced sterilization of the 400,000 Germans considered genetically or morally unhealthy people, while others were the material executors of the euthanasia program against incurable mentally disordered patients. From the beginning of the Nuremberg trials, the behavior of scientists during the Third Reich was a subject of reconstructions, but also of justifications by the protagonists themselves. The prosecution of the International Military Tribunal argued that some of the scientists were willing executioners in the service of the Nazi regime, and when all Jewish or politically democratic and or liberal scientists were expelled from their jobs, no outcry was raised. Some emigrated abroad so as not to contribute to the success of the regime, even if most of the researchers did not follow orders, but worked at full speed and with personal commitment to solve problems related to science. So, at the end of the war, in some sectors, for example in research on aerodynamics at ultrasonic speeds, German scientists were the world's pioneers. After the discovery of atomic fission in 1939, they scrambled to develop possible technical uses for this new discovery, including nuclear devices, and towards the end of the war, one of the teams, that of the Gotov military laboratory, even managed to develop and test a nuclear bomb, but the German bomb came nowhere near Hiroshima-like power, and the Nazi nuclear program failed. It is only thanks to Fermi and Oppenheimer that the construction of the atomic bomb was possible. When Enrico Fermi returned to Italy in 1927, he occupied the chair of theoretical physics in Via Panisperna. He tried in every way possible, together with Corbino, to transform the institute into an avant-garde center on a world level. The young scientist needed suitable collaborators, and the first to be hired was his friend Franco Rasetti, who was assigned the task of carrying out research in the field of atomic physics. Corbino, later, during a lesson at the Faculty of Engineering, announced the availability of some places within the school, and between 1927 and 1928, Emilio Segre, Eduardo Amaldi, and Ettore Majorana joined the research group. Fermi had obtained, thanks to the support of Corbino, his own school made up of very young students, where through informal, often improvised seminars, he taught his students the secrets of modern physics. The Panisperna group continued their work until 1935, when they partly dispersed to take care of other schools or escape from the war. Rasetti said of that period, "The activity of the years between 1927 and 1931 took place almost entirely in the field of atomic and molecular spectroscopy, also because we knew the technique well and had suitable instruments. Fermi participated in the experiments and in the theoretical interpretation of the results. He was not, nor was he ever, an experimenter refined in precision techniques, but he had a very acute intuition of which experiments were crucial for solving a given problem, and he went straight to the goal without caring about inessential details. Similarly, in theory, he availed himself of whatever means most directly led him to the result, making use of his mastery of analytic means if the case required it, otherwise resorting to numerical calculations, heedless of mathematical elegances. In 1929, Fermi and Rasetti understood that their research on spectroscopy was about to come to an end. The new objective of the group then became the study of atomic nuclei. And on March the 29th of the same year, Fermi was nominated by Mussolini as a member of the Royal Academy of Italy, becoming a member of the Fascist Party. Thanks to this important step, the scientist tried to obtain funding for his institute, which came through funds from the National Council, with an average value 10 times higher than that of other institutes. Together with Rasetti and Corbino, Fermi made sure the funding was distributed well, concentrating it on the study of nuclear physics and cosmic rays. When he focused his research on the atomic nucleus, it was already known that most of the existing nuclei were of a stable nature, while others were radioactive, and their task now was to study the forces that hold the nucleus together and understand the mechanism linked to the emission of radioactive particles. In order to better understand what was missing in their research, in 1931 Corbino and Fermi organized an international congress on nuclear physics. Thanks to the Accademia d'Italia and the National Research Council, of which Fermi was secretary of the physics committee, the congress was financed with 200,000 lire, a huge sum for the time. At the event, which was opened with a speech by Mussolini and which was attended by the world's greatest scientists, Fermi expressly asked to present not only the problems they had already solved, but above all the unsolved ones, thus becoming a catalyst of ideas in which they focused on still open theoretical and experimental questions. The Congress ended with the following words from Corbino. I think that the future trend of nuclear physics will be greatly influenced by this week of common life, the profound results of which will perhaps be seen in all the works that will mature in this field for several years. And this was the main purpose that the promoters of this conference, myself first, had in mind. His prophecy came true, and Fermi, 3 years later, wrote the theory of beta decay, which describes the mechanism relating to the radioactive decay of the atomic nucleus. This theory earned him the Nobel Prize in Physics. Fermi's group began intensively working on artificial radioactivity when Irene Curie and her husband Frédéric Joliot discovered it in January 1934. Back in their laboratory in the autumn of the same year, Fermi and Rasetti began building the instruments needed to study the radioactivity, and contrary to what was done by Curie and Joliot, they decided to bombard target nuclei with neutrons, neutral charges, instead of alpha particles, positive charges. Using radon and beryllium neutrons as sources, Fermi began to bombard the elements of the periodic table in a systematic way, and only when he arrived at fluorine and aluminium did his Geiger counter finally produce its first results. Fermi worked intensely on the new research, and given the need for profound knowledge in chemistry, he decided to hire an expert in radiochemistry, Oscar D'Agostino. The work proceeded rapidly, and the results were sent and published immediately. In a short time, the group irradiated about 60 elements with neutrons, and at least 40 were identified as new radioactive elements. During the classification phase of the reactions, the group realized that neutrons gave rise to the formation of new radioactive nuclei in virtually all irradiated elements, regardless of their atomic number. These results soon went around the world, and their discovery was confirmed by the leading physicists of the time. In the second half of 1934, the group then decided to move from a qualitative study of the radioactive properties of materials to a quantitative one. The study, assigned by Fermi to Amaldi and Bruno Pontecorvo, who had recently joined them, had as its primary objective that of obtaining easily reproducible results, but the two scientists ran into enormous difficulties. The properties of the various metals seemed to strongly depend on the materials on which the neutron source and the irradiated sample were placed. On the morning of October the 20th, 1934, everything was ready for a systematic experiment. Amaldi had built the chamber with lead walls, and repeating the measurements several times, he bombarded a target consisting of a sample of silver with neutrons, inserting a lead wedge between the source and the target in order to distinguish the absorbed neutrons from the diffused ones. In physics, the cases in which discoveries and inventions are the result of a fortuitous event are not uncommon. Among these many cases, one occurred precisely that morning. Fermi was alone in his laboratory, while his collaborators and students were engaged in lessons and exam sessions. Impatient and restless, he decided to start the procedures immediately, but an instant before starting, he replaced the lead wedge with a piece of paraffin. The results on the induction of artificial radioactivity were completely unexpected. The paraffin, a substance rich in hydrogen, that is, in protons, slowed down the incident neutrons, amplifying the effectiveness of the artificial radioactivity. The experiment was repeated with water, also rich in protons, and obtained the same results. Emilio Segre remembers, "At first, I believed that a meter had simply failed. But it didn't take long to convince each of us that the extraordinarily strong radioactivity we were witnessing was real and resulted from the filtering of primary radiation by the paraffin. We went home for the usual siesta, still surprised and confused by the morning's observations. When we returned, Fermi had already formulated a hypothesis to explain the action of the paraffin. Fermi defined slow neutrons. The neutrons were slowed down in a series of elastic collisions with the protons of the paraffin, thus increasing their effectiveness in causing artificial radioactivity. Fermi demonstrated how the probability of capturing neutrons and producing nuclear reactions increased with decreasing neutron speed, which was unexpected for the time, given that it was believed to be the other way round. It is not clear why Fermi used paraffin, and how he had this apparently bizarre intuition. Not even the great scientist himself was able to find an answer, and he was certainly the most surprised of anybody involved. Corbino then convinced Fermi and the group to patent the process of producing artificial radioactive substances. This patent, which bears the date of the 26th of October 1935, was an important step in the construction of the atomic bomb. In the summer of 1935, the group began to disperse. Italy's general political situation was deteriorating, and the country was preparing for war with Ethiopia. As a reaction to the heavy political climate, the work rate of the scientists became frenetic. Amaldi, Fermi's collaborator, who contributed years later to the creation of the National Institute for Nuclear Physics, the NINP, the European Organization for Nuclear Research, CERN, in Geneva, and the European Space Agency, the ESA, stated, "We started at 8 in the morning and made measurements practically without interruption until 6 or 7 in the evening, and often even later. We carried out the measurements according to a chronometric schedule, since we had studied the minimum time necessary to carry out all the operations. We repeated them every 3 or 4 minutes for hours on end, and for as many days as needed to reach a conclusion on any particular point. Once a given problem was solved, we immediately attacked another one, without any interruption or uncertainty. Physics as a somme was the expression we used to talk about our work, while the general situation in Italy was getting more and more gloomy. The discovery of slow neutrons definitively consolidates the fame of the Fermi group worldwide, and at that point a particle accelerator would have been necessary to carry out the studies in a more in-depth way. Fermi, realizing its importance, wanted to equip the group with a machine like this, but soon found himself in unfavorable conditions. In the summer of 1935, Rasetti was sent to visit Robert Millikan's laboratory in Pasadena and the radiation laboratory in Berkeley to study and reproduce the performance of the plants built at those laboratories. In Pasadena, Rasetti studied a high-voltage accelerator developed by a student of Millikan's, while in Berkeley he studied the cyclotron, invented by Ernest Lawrence. Back in Italy, Fermi and Rasetti abandoned the idea of building a particle accelerator due to the high cost. Towards the end of 1936, the Italian political situation deteriorated further, with the Rome-Berlin axis. Mussolini's fascist Italy and Hitler's Nazi Germany had united. The final blow to the study group comes on January the 23rd, 1937, when Cogbino suddenly dies of pneumonia. Fermi would have been the natural successor at the helm of the institute in Via Panisperna, but through political maneuvering, Professor Antonino Losurdo managed to take the place of the deceased professor. With the annexation of Austria to Nazi Germany, the European situation worsened rapidly, and in July 1938 the anti-Semitic campaign began in Italy as well. There was the publication of the Race Manifesto and the subsequent racial laws, for which Fermi had to give up the collaboration of some of his assistants. Laura Capon, the wife of the physicist, had Jewish origins, and the two were subjected to racial persecution. The woman recalls in her book, Atoms in the Family, that the couple decided to leave Italy following the implementation of those laws. On November 10th, 1938, the professor received, at the age of only 37, the official announcement of the awarding of the Nobel Prize. Fermi decided that following the awarding of the prize in Stockholm, he would sail with his family to the United States, and from that moment on, he would only return to Italy a few more times. Columbia University in New York had invited him for a series of lectures, and on January the 25th of the same year, he was part of an experimental team in the university basement, where he conducted the first nuclear fission experiment in the United States. In a speech given in 1954, at the end of his term as president of the American Physical Society, Fermi recounted the beginning of the project. I remember very vividly the first month, January 1939. In that period, Niels Bohr was on a lecture engagement at the Princeton University, and I remember one afternoon Willis Lamb came back very excited and said that Bohr had leaked out great news. The great news that had leaked out was the discovery of fission, and at least the outline of its interpretation. Then, somewhat later that same month, there was a meeting in Washington where the possible importance of the newly discovered phenomenon of fission was first discussed as a possible source of nuclear power. After Albert Einstein's famous letter of 1939 to President Roosevelt, written by Leo Szilard, in which, in the face of the threat posed by the Nazi regime, the possibility of building an atomic bomb was highlighted, the Navy established a fund of $6,000 for Columbia University, a fund that was later increased for the Manhattan Project. After moving to Chicago, Fermi began construction of the first nuclear reactor, Chicago Pile 1. It was Fermi who solved the first great scientific obstacle of the Manhattan Project on December 2nd, 1942, at 2:20 p.m. local time, when, under the bleachers of the stadium on the campus of the University of Chicago, the group he led gave birth to the first self-sustained nuclear chain reaction, initiated in the CP1, creating what is considered by all to be the start of the nuclear age. A coded message, "The Italian navigator has just landed in the New World," was sent by General Groves to President Roosevelt to advise him that the experiment had been successful. After Germany's surrender on May 8, 1945, the doubts of the Manhattan Project scientists grew in intensity. In Chicago, in the days immediately following the end of the war in Europe, Arthur Compton appointed a committee to deal with the question of the use of the bomb. It was made up of various scientists from the metallurgical laboratory, including Szilard himself, and chaired by James Franck, a German physicist who immigrated to the United States to escape anti-Semitic persecution. In June 1945, the final report, known as the Franck Report, although drafted for the most part by Szilard, was urgently delivered to War Minister Henry Stimson for him to forward it to President Truman. The report advised against the use of the atomic bomb against Japan. A bloodless demonstration of the new weapon was suggested. When no response came, Szilard decided to write a petition to President Truman, which he circulated among the scientists of the metallurgical laboratory, collecting 53 signatures. He sent copies to the Oak Ridge and Los Alamos labs with a cover letter in which he wrote, "However limited the possibility that our petition could affect the course of events, I personally feel that it would be important if a large number of scientists who have worked in this field were to speak publicly with clarity and confidence about the opposition on moral grounds to the use of these bombs in the present phase of the war." But at Los Alamos, Szilard's petition was not circulated. Sent through institutional channels, the petition never reached Truman because the question of the use of the bomb had already been fully addressed and resolved by the competent authorities. The decision was also made at the highest political level by Fermi and other scientific leaders shortly after the German surrender. Truman had created a special commission, known as the Interim Committee, to address the question of the possible use of the atomic bomb, and in which the most important scientists of the Manhattan Project participated, including Vannevar Bush, a man whose name appeared years later on the Majestic 12 roster. The scientific commission, formed by Oppenheimer, Fermi, Lawrence and Compton, had the very delicate responsibility of giving technical advice on the use of nuclear weapons. In a formal report, the scientists wrote, "The opinions of our scientific colleagues on the initial use of these weapons are not unanimous. They range from the proposal of a purely technical demonstration to that of the military application, best designed to induce surrender. Those who advocate a purely technical demonstration would wish to outlaw the use of atomic weapons, and have feared that if we use the weapons now, our position in future negotiations will be prejudiced. Others emphasize the opportunity of saving American lives by immediate military use, and believe that such use will improve the international prospects, in that they are more concerned with the prevention of war than with the elimination of this specific weapon. We find ourselves closer to these latter views. We can propose no technical demonstration likely to bring an end to the war. We see no acceptable alternative to direct military use." The Interim Committee, made up of scientists, industrialists and military personnel, unanimously approved the following measures. 1. That the weapon be used against Japan at the earliest opportunity. 2. That it be used without warning. 3. That it be used on a dual target, namely a military installation or war plant surrounded by or adjacent to homes or other buildings most susceptible to damage. On August the 6th, 1945, at 8:15 in the morning, the first atomic bomb in history was dropped on Hiroshima. 3 days later, on August the 9th, 1945, at 11:02, a second bomb was dropped on Nagasaki. Shortly after, Japan signed the surrender, and the historical theory handed down in the West was that bombing, terrible as it was necessary to dominate an aggressive power and put an end to the war. A truth that was contested, since Japan was already on its last legs and had sent signs of wanting an armistice. More than 210,000 dead and 150,000 injured were counted, without bearing in mind the long-term damage produced by radiation, which we are still studying in the medical field. Fermi was elected a member of the United States National Academy of Sciences in 1945. At the end of the war, he was offered the professorship of physics at the University of Chicago, becoming a fellow for nuclear studies. The Manhattan Project was replaced by the Atomic Energy Commission, the AEC, on January 1st, 1947, and Fermi served on the General Advisory Committee, chaired by Robert Oppenheimer. After the detonation of the first Soviet nuclear fission bomb in August 1949, Fermi strongly opposed the development of a hydrogen bomb on both moral and technical grounds. After making a few short visits to Italy, on November 28, 1954, Fermi died at the age of just 53 of stomach cancer. A couple of years after the explosion of the 2 atomic bombs on Japan, the Roswell case of 1947 became the first historically recognized event related to aliens. And 4 years before he died, while having lunch with some colleagues in the Los Alamos laboratory, Fermi took those present by surprise with a question. But where is everybody? He was referring to extraterrestrials. There are at least 100 billion galaxies in the universe, each containing up to 1,000 billion stars, and on this basis there should be trillions and trillions of planets, some of which are potentially habitable. The question, renamed the Fermi Paradox, explains the apparent contradiction between the probability that ours is not the only intelligent life form in the universe and the absence of established contacts with extraterrestrial civilizations. It has often been used to put doubt on the Drake equation, the mathematical formula according to which the universe is rich in galaxies, stars and planets, and therefore in advanced civilizations capable of communicating with us. It thus followed that Drake's estimates are either wrong, or more likely, our observation and understanding of the universe is still incomplete. Fermi's question arose from the same primary observations of the Drake equation. There are many stars in the universe. It is very old, and therefore there should have been enough time for the birth of other intelligent species in remote places of the universe, before the birth of man on Earth. But the question itself has many obstacles. The first one that Fermi considered was the distance between the stars. For example, while Voyager travels at a speed of 61,500 km an hour, it could only reach the nearest stars in a few tens of thousands of years. A very long time compared to the life of a human being, but very short compared to the age of the entire universe. Fermi's explanation is natural. There is no time to reach other planets, other destinations. There is no time to communicate, and there is an immense problem of synchronicity, because any communications or exchanges should take place more or less in the same epoch, but due to the distance between planets, this could never be possible. So, if a space civilization had sent probes or messages millions or even billions of years ago elsewhere in our galaxy, this civilization would have had enough time to complete the feat, even long before our appearance on Earth. Fermi thus formulated two main hypotheses. The first says that the Earth has never been visited by other intelligent civilizations that appeared long before ours. The second says that a form of life, somehow more advanced than we are, has left no evidence of communications between one star and another, because when we look around the universe, it appears quite silent. Three categories were then distinguished. The first, simplest category says that intelligent life in the universe is extremely rare. There aren't many advanced civilizations out there that can either communicate or send probes to explore the universe, simply because the emergence of life is hard enough, and the biological evolution needed to develop complex intelligent life forms, evolved enough to be able to reach us in some way, is very complicated, and therefore the result is that there are few of them. This category says that what happened on our planet would not be so common in the rest of the universe, while we assume that our evolutionary situation is an average one, that there is nothing particular about us. Obviously, we don't know the probability of the appearance of life on another planet. We don't even know what the probability is that there are truly habitable planets in the universe. Obviously, we know that there are some similar to the Earth in terms of characteristics, but we don't know how suitable they are for the appearance of life, and we even only partially know what could have caused life on our planet. For example, according to the Darwinian evolutionary theory, the human being is a close relative of the monkeys, and before reaching our current form, we had to undergo various genetic mutations dictated by environmental change and the context we were living in. But we don't know if other forms of life can develop in other environmental and chemical conditions. According to some scholars, finding a planet with characteristics suitable for life, like our Earth, would be extremely rare, even if there are many planets in the universe. We are also talking about intelligent life, therefore not about life in general, but about species that are able to communicate, to send probes over gigantic distances, and the appearance of intelligent species on Earth took billions of years. So, according to the first category, it seems that it's not very frequent that intelligent species appear out there in the universe. The second category of explanations is slightly different and assumes that intelligent life is not rare. Life could appear with a certain frequency, even relatively common, and in the history of our galaxy there could be many other intelligent species capable of developing technology for communication over interstellar distances, able to explore space, and so on. But all these intelligent species would not actually have a very long lifespan. In other words, in this category there is always some natural phenomenon where conflicting forces lead to the extinction of intelligent species, or even some form of self-destruction, whereby the species, once it reaches a certain stage of development, ends up collapsing on itself and disappearing. There is also another view, which is always part of this category, but which is slightly different. That is, it is not that they don't last long because they become extinct or because they self-destruct, but they don't last too long because they transform into something else and no longer feel communication is needed. The third category instead says that these extraterrestrial forms exist and that there are also many of them, but either they do not want to be seen, or they are not easily observable, or that they have been here but have left no trace, and so on. And it's all those famous explanations that are also talked about in science fiction, as in the theory that intelligent species are hidden in the shadows because they are afraid of being discovered, of being attacked by other more advanced forms, and so on. However, the problem with this category of explanations is that they are often neither scientific nor useful. They cannot be proven or disproven, which goes against one of the fundamental principles of developing a scientific hypothesis. Therefore, we cannot determine whether these explanations are more or less false. While they are interesting to consider, we must treat them as untestable hypotheses and outside the realm of conventional science. So, in reality, all these types of explanations remain partial and do not really explain how things are, and they tell us that we are simply not able to find an answer yet. There are many preconditions that must be met for everything to go right. In addition, if this happens, one must face many difficulties and overcome many obstacles in order to see the rest of the universe. On the other hand, the degree of technological development necessary to embark on an enterprise such as colonization of the galaxy or even simple interstellar exploration must necessarily be very advanced. We ourselves are just getting started, and we still have a long way to go before thinking that we can reach other stars or galaxies. Our body, on a biological level, is not made to survive for a long time in the universe. For example, remaining in a spaceship for a long time, exposure to cosmic rays could cause significant health problems and even death in a short time if this energy is not shielded adequately. Cosmic rays are made up of highly energetic particles from deep space, such as gamma rays, and prolonged exposure to these rays can damage the cells of our body, affecting the proper functioning of vital organs and causing diseases such as cancer. However, any answer to the question that the paradox poses will come from a balance between how common intelligent life is in the universe and how common its biological cycle is. These factors remain quite important, since if intelligent life is extremely rare, we could be alone in the universe, and the sightings that are currently made in all parts of the world could have a very different nature from what we believe. With regard to the theories related to creation, there was also another man who underlined a vision determined by the continuous change of the universe, and who tried to put a doubt in Einstein's mind. Had he considered the power of the electromagnetic force present in space in his theory of relativity, obtaining a resound and firm response from Einstein himself. Emanuel Velikovsky was a Russian doctor of Jewish origin who moved to the USA in 1939 and met Einstein by chance. When Einstein died in 1955, on his bedside table one of Velikovsky's books was found, Worlds in Collision, that no one would have ever thought capable of attracting Einstein's attention. Which in a certain sense is true, since the book was delivered to him personally by Velikovsky some days after its publication. Velikovsky began to study astrophysics, religion and history, and with his book he became the bête noire of scientists from all over the world, raising the biggest scandal that had ever involved the scientific community since Galileo, and arousing a gigantic crusade by the most authoritative scientists in America, who, in 1950, even blackmailed magazines and the book's publishing house to prevent its publication. It was only the beginning of the war that the scientific community declared on the author, and in which numerous universities, associations and authoritative journals took the field. In his book, he offered the explanation in scientific terms of some of the miracles of the Bible, and this would have already been enough to upset the common thought of the time, but also an incredible historical reconstruction of the evolution of the solar system, and this could not be tolerated by official science. The central idea of the text was that 1500 years before Christ, in historical times, a large mass had detached from the planet Jupiter, which went on to form a gigantic body defined as extraterrestrial, and that over 7 centuries, with a cadence of 52 years, would have come ever closer to the Earth, causing earthquakes, floods, electromagnetic storms, meteor showers and climatic upheavals. Cataclysms that would have greatly influenced the culture and events of our ancestors, of which traces would be found in the myths and documents that have been handed down to us, and which, according to the author, would exist in almost all the populations of the planet, from the Mayas to the Chinese, from Polynesians to American Indians. The first of these contacts would have occurred in 1500 BC, and in its approach, the wayward comet caused what in the Bible are described as the 10 plagues of Egypt, which, examined one by one, are subjected to a scientific explanation, in quotation marks. For example, the same crossing on foot of the Red Sea would have been possible thanks to the incredible tide caused by the attraction of the nearby comet, and on that occasion the rotation of the Earth underwent a considerable slowdown, which led to thick darkness in Egypt for 3 days, the famous 3 days of darkness of many modern prophecies. After about 50 years, the comet returned, causing a new slowdown in the rotation of the planet and an oscillation of the Earth's axis. The Sun seemed to stop for an estimated time of 18 hours, an event which, in the mind of the author, would be configured as the famous miracle of Joshua, who orders the Sun to stop, and which stops for an entire day. These approaches were repeated every 50 years or so, with no more disastrous consequences until 747 BC, the year in which an incredible series of events took place. The orbit of the comet, perhaps due to a collision with another, changed until it collided with Mars, and the two planets settled into their present orbits. Mars was pushed towards the Earth and came close to it several times, the last of which in 687 BC, a period in which the solar and lunar movements were upset, and with them the seasons and the passage of time. Velikovsky hypothesized that it was for this reason that our ancestors needed many and continuous changes of the calendar until the year settled at 365 days, 5 hours, 48 minutes and 46 seconds. Velikovsky was labelled a rookie, but from time to time some authoritative scientist would come up with evidence that would substantiate, at least in part, some of his unscrupulous but suggestive hypotheses, making them plausible. Science in the 1950s deemed it unacceptable that what keeps bodies in orbit in our solar system was not necessarily the force of gravity, as Newton had taught us, but another force, electromagnetism, of which gravity would only be an aspect. Electromagnetism itself soon became the subject of long epistolary conversations between the writer and the famous scientist. To this day, no one has yet managed to combine gravity with electromagnetism exhaustively through the unified field theory, and only 2 people have tried, Einstein and Velikovsky. Albert Einstein, the father of the general theory of relativity, spent most of his life trying to develop a unified theory that would combine gravity with the other fundamental forces of the universe, without finding a complete solution before his death. However, some of the predictions that Velikovsky made, such as, for example, the very high temperature of Venus, became real. Recent observations and space missions have in fact revealed that the temperature of Venus is higher than previously thought. In the past, Venus was believed to have a similar temperature to Earth, but thanks to more precise measurements, it has been found that the surface temperature of Venus is extremely high and around 462 degrees Celsius or 864 degrees Fahrenheit, which would make it the hottest rocky planet in our solar system. This would be attributed to several factors, such as the intense greenhouse effect caused by the dense atmosphere. Composed mainly of carbon dioxide, which traps heat, the atmosphere of Venus would also be characterized by a dense layer of clouds of sulfuric acid, which further contributes to the increase in its temperature. The sulfuric acid clouds would absorb the sun's heat by holding it in the upper atmosphere, thus preventing the heat from escaping into space. Research to fully understand why the planet is so hot also continues today, in order to understand the possible outcomes of the greenhouse effect on other planets and on climate change in general. Velikovsky also spoke of the effect of the force of gravity that binds the Moon to the Earth, the magnetic storms on Jupiter, the theory that comets have detached from larger bodies, and many other observations which were only later confirmed, including the theory that the large anomalies in the rotation of Venus are due to its recent installation in its orbit. Venus would be the only planet that rotates in the opposite direction to all the others in the solar system. Most planets spin anti-clockwise when viewed from the north celestial pole. However, Venus rotates slowly clockwise, which means that its sun rises in the west and sets in the east. This phenomenon, called retrograde rotation, is still being studied today by scientists trying to understand its causes. In practice, therefore, worlds in collision start from the hypothesis that the events of a clearly catastrophic nature described in ancient literature, and in particular the Bible, are phenomena that actually occurred, and whose explanation cannot be given in a purely terrestrial context. It must be attributed to interactions between planet Earth and possible extraterrestrial bodies. The book contains criticisms of traditional astronomical scenarios, where virtually only the force of gravity is taken into consideration, at the expense of possible electromagnetic effects between celestial bodies, both on a large scale and in close encounters between these celestial bodies. Many years after worlds in collision, it can certainly be said that there is now greater attention from scholars in the field of natural sciences towards ancient catastrophic traditions. This attention also depends on the possibility offered by today's tools that were not previously available, which are capable of verifying the effects of events at the geological and biological level, such as the analysis of pollen deposits or other biological components in lake and ocean sediments, the analysis of organic and inorganic substances in glaciers, and dendrochronology that dates and studies the annual growth increments of trees, or tree rings. From these studies, evidence has emerged of considerable climatic variations in the last 12,000 years, which occurred so rapidly as to be difficult to explain in terms of normal terrestrial processes. The verification with the Shoemaker-Levy comet and the direct observation of the impact of the fragments of this comet on Jupiter, for example, an event never before considered by astronomy, has made us much more aware that we are in an environment, the solar system, richer in dangers than thought 50 years ago. Although some of Velikovsky's different observations have found answers in the astronomical field, and the theory of Mars and Venus would still be unacceptable by many astrophysicists, the questions relating to electromagnetism and the force of gravity, however, open yet another dilemma. Who knows if Velikovsky ever wondered whether an electromagnetic energy generated by atomic bombs could cause such a disturbance as to become a signal for aliens or create problems also connected to gravity itself. A nuclear bomb works through nuclear fission or nuclear fusion, processes involving the nucleus of atoms, and which mainly generate a large amount of thermal energy, light and ionizing radiation, and it is possible that nuclear explosions have indirect effects on the Earth's magnetic fields. For example, a powerful atmospheric nuclear explosion capable of producing a large amount of ionized plasma can interact with the Earth's magnetic field, causing temporary perturbations. This phenomenon is known as a nuclear electromagnetic pulse, or NEMP, which can be generated by either a nuclear bomb detonated in the atmosphere at high altitude or a nuclear weapon detonated in space. There are two main types of NEMPs. E1 is the first electromagnetic pulse produced immediately after the nuclear explosion. It is mainly caused by the direct interaction of gamma rays with the atmosphere, has a rapid effect, and can generate very strong electric and magnetic fields. It is especially harmful to sensitive electronic systems and can cause permanent or temporary damage to electronic devices. E3 is a long-term electromagnetic pulse that occurs after the nuclear explosion. It is caused by the interaction of the nuclear explosion with the Earth's magnetic field, has a longer lifetime than E1, and can induce long-lasting effects on electric currents in electrical and transmission systems. It can cause significant damage to electrical infrastructure, such as power supply networks and long-distance communication systems. It is important to underline that nuclear electromagnetic pulses are complex phenomena, and their characteristics depend on various factors, such as the altitude of the explosion, the power of the nuclear weapon, and atmospheric conditions. Nuclear bombs intended to generate NEMPs are specifically designed to maximize the effect of the electromagnetic pulse, but all nuclear explosions, regardless of their purpose, can generate some form of NEMP. Also, underground or ocean-based nuclear explosions can cause small local variations in the Earth's magnetic field, but these effects are usually transient and limited in scope. In summary, nuclear explosions can have indirect effects on the Earth's magnetic fields through phenomena such as the nuclear electromagnetic pulse, and radiation can generate a magnetic field. These fields are generated by the oscillations of the electric charges in the atoms or molecules that emit both ionizing and electromagnetic radiation. This can generate a magnetic field due to the movements of the charged particles that it is composed of, and a charged particle, such as an electron or a proton moving through space, generates a magnetic field around itself. For example, ionizing radiation, such as X-rays, gamma rays, or high energy charged particles, consists of charged particles moving at high speed. Consequently, when these particles pass through a space, they generate magnetic fields associated with their movements, or when an electron beam is accelerated in a cathode ray tube, a magnetic field is created around the path of the electrons. This principle is used in devices such as old televisions, where the magnetic field deflects electrons to form the image on the screen. Also, electromagnetic radiation, such as visible light or radio waves, consists of electric fields and magnetic fields that propagate through space. So, we are sending very specific signals to the universe. Who knows if with new future research, the universe will answer. However, we should note that the events related to the Roswell incident occurred approximately 2 years after the explosion of the second atomic bomb. So, if that Roswell UFO crash were a true historical episode, it could be that aliens are much less distant from us than we currently think, but above all, that they are listening to us, given that we are sending out these precise signals to the universe.